Hi, and welcome back to our APES flipped classroom. We're continuing with Unit 4, and today we are talking about soil. So we'll cover both soil formation and erosion, as well as characteristics of soil and soil tests. So let's jump right in. So obviously, when we're talking about soil, first we need to talk about what it is, how it's categorized, how it's formed, and the services that soil itself provides. And so first thing that we're going to talk about is what soil is, and we'll come back to this and talk about it in detail, but just in general, it is a mix of abiotic components, so things like sand, silt, and clay. That's the broken down parent material. That's the geologic components, broken down rock, and organic components, which are living or were once living. And so that is the main organic material in the soil, usually called humus. That is broken down biomass, like leaves, dead animals, waste, all of those things that are broken down by our decomposers. As a result of that decomposition by decomposers, we also have all of our nutrients, both ammonium, nitrates, phosphates. And then, of course, also in our soil, we're going to have water, we're going to have air, and you're going to have living organisms. So soil provides a lot of services to its ecosystem. These are not ecosystem services, but these are services that the soil provides to its ecosystem. The first and the most obvious is that for plants, it anchors their root structures, it provides them with water, it provides essentially shelter, a place to anchor the roots. It provides all the nutrients needed for growth, the nitrates, potassium, phosphates, magnesium, all of the things that plants need for growth, including those micronutrients. It also, and this is probably one of the key factors of soil, filters water, whether that's rainwater or runoff, because as the water percolates through the soil, pollutants are going to get trapped in those pore spaces. They're going to get picked up by plant roots. And so in the process of percolating through the soil, water gets cleaner. And so the water that enters our aquifers and our groundwater systems is cleaner than the water that hits the soil to begin with. Soil also provides nutrient recycling. Soil is home to decomposers that break down that dead organic material, and they return those nutrients to the soil. And then, of course, soil also provides a habitat for lots of organisms, earthworms, fungi, bacteria, those very important nitrifying bacteria that we've talked about as part of the nitrogen cycle, moles and voles, even slugs. All of those organisms live in the soil and are vital to all of the processes that happen in soil. Okay, so how does rock become soil? So there's two processes that take place. And the first process is what we call weathering. And there are three kinds of weathering. And weathering overall is just the breakdown of rock into smaller pieces. And so the first process by which this can happen is what we call physical weathering. So that's wind and rain, the freeze-thaw cycle of water. When it freezes, ice is less dense, so it expands, it cracks the rock. As it thaws, then those little pieces of rock break away. There's also biological weathering, where the root systems of plants push their way into rocks and they crack the rock, and that also contributes to weathering. We see this very often with big plants like trees, but you'll also see it with really small plants. If you take a look around as you're walking, you'll see small plants in little tiny spaces, and they filter their roots down into those little spaces. And as the plant grows and the roots grow, they expand, and that cracks the rock. The third type of weathering is what we call chemical weathering. And we can have chemical weathering that occurs because of lichens and mosses. You might remember that those are part of the primary succession, and you might remember that they're very critical because lichens and mosses can excrete acid through their root systems, and that acid helps to break down the rock and contribute to that chemical weathering. We also have chemical weathering that's a result of acid rain. Now, rain is naturally acidic. Our rainwater is always going to contain some sulfates and nitrates, which of course, when they combine with water, are going to make sulfuric acid and nitric acid. Humans are also contributing to acid rain through our combustion of fossil fuels, which adds to the nitrates and the sulfates in the atmosphere, and that contributes to acid rain. And the acidity of that rain contributes to the chemical weathering of rocks. Weathering of rocks is part of soil formation. We don't have soil formation without the breaking down of parent material. So the first piece is this weathering. It's broken down into smaller and smaller pieces. And then those small pieces can be carried away by erosion and then deposited by erosion. So there's more weathering that will occur, more breaking down that will occur in the process of runoff, and then also tumbling in streams and rivers. And so erosion is that transport of those weathered rock fragments by wind and rain. And so the soil, not yet soil, the broken down rock is picked up by the water, transported by the water, and when it reaches a flatter area or the bottom of a river or lake or stream bed, then we get deposition. So when it reaches a flatter area and the water is not flowing as quickly, then it's going to get deposited. Okay, so let's talk about how soil is formed. So there's two pieces that lead to soil formation. The first one is the weathering of the parent material that produces those smaller and smaller fragments that make up that abiotic portion of the soil, the portion of the soil that is not living and has never been living. And that's the minerals, that's the rock content. These are the sand, the silt, and the clay, those three abiotic components of soil. And so that can be weathering in place, or it can be weathering and then erosion and deposition. From above, though, we have the breakdown of organic material. So we talked about lichens and moss that help to break down the rock, but then we also said that when they die and decompose, that contributes the organic material. So soil without organic material is not soil, it's just broken down rock. We have to have both components, both the organic that we call humus and the inorganic, the parent material, and the two of them together is what we call soil. And then of course, erosion is going to deposit soil particles from other areas, and that's going to add to our soil. So the type of soil formed depends on a lot of different things. Our parent material is significant here. So depending on the type of rock that is being broken down, that's going to affect the pH of the soil and also therefore the nutrient content of the soil. More acidic soil is not as effective at retaining nutrients. And so soils that are based on calcium carbonate types of rocks, so usually sedimentary rock, tend to be better at retaining nutrients. Topography also affects what type of and how rich our soil is. If you have a very steep slope, you're going to have a lot of erosion. And so all of the humus, the organic material, is going to get carried off. If we have more level ground, we're going to have more deposition and more decomposition happening because the soil stays in place for longer. Climate also affects soil formation. If we have a warm climate, we're going to have faster breakdown of that organic material. So it's generally going to have a more nutrient-rich soil. And colder climates are going to have less nutrient-rich soil because you're not going to have as much decomposition. Now, take that with a grain of salt, because we know that one of the biomes that is the warmest, the tropical rainforest, is very nutrient poor soil, but that's because the nutrients are pulled out of the soil just as quickly as they are decomposed and returned to the soil. But in general, a warmer climate is going to have faster breakdown of organic material, and therefore it's going to have more nutrient-rich soil. If you have a climate that has higher levels of precipitation, you're going to have more weathering, so you're going to have more breakdown of parent material. You're also, again, depending on topography, going to have more erosion, potentially more deposition. So precipitation can have both a beneficial and a negative impact on soil formation. And then, of course, the organisms that exist there are going to have significant effects on soil formation. If you have lots of decomposers and detritivores that are able to break down that organic material, then you're going to have a richer soil. If you have few organisms, then you're going to have a less rich soil. Okay, when we talk about soil, we talk about horizons. These are the different layers within the soil. So the very topmost layer we call the O horizon, and this is a layer of organic matter. So this is plant roots, this is dead leaves, this is animal waste. This is really, generally speaking, kind of on top of the soil. It does provide nutrients, it limits water loss to evaporation, but it's not technically soil yet because it hasn't really broken down. It's still considered the organic horizon. The A horizon is what we typically call topsoil. This is mostly decomposed organic material and minerals from the parent material. So this is that mixture of the biotic components from the decomposed humus and the abiotic components from the parent material. The A horizon has the most biological activity. This is where we're going to find those nitrifying bacteria. This is where we're going to find all those detritivores and some of our decomposers. And they're busy breaking down all of that organic material to release the nutrients. Below the A horizon, we have the subsoil or the B horizon. And this is a layer below the topsoil. It is mostly mineral, very little biotic content, very little organic matter. It does contain some nutrients, but not much. And the C horizon is the least weathered soil. It is closest to being the parent material. This is sometimes called bedrock. We will, in usually acidic soils, see an E horizon, which is, it stands for alluviation horizon, that will usually occur below the A horizon. It's a very light layer in color, and it's an area where because of the acidity of the soil and moisture penetration, most of the minerals and nutrients have alluviated. They have run off with the water. Not all soils have an E horizon. It will sometimes be between the O and the A. It's more often between the A horizon and the B horizon. Okay, so we've talked about what soil is. We've talked a little bit about why it's important. Now we're going to talk about some of the things that make soil less valuable, that degrade our soil. And when we talk about soil degradation, we're talking about the loss of the ability of soil to support plant growth. So soil degradation frequently does impact the ability of soil to filter water. But when we talk about degradation, we are usually specifically focused on the inability to support plant growth. So what are some of the things that lead to soil degradation? Well, loss of topsoil, so that A horizon that contains all of the nutrients, all of the organic material. If we lose that, then it dries out the soil. It takes the nutrients and the soil organisms that recycle nutrients, and it makes the soil less able to support plant growth. Topsoil can be lost through tilling of dry land, because when we till, and you can see in this picture, when we till and then there's dry air, that soil can actually just blow away. You might remember hearing about the Great American Dust Bowl of the 1930s, when there were huge dust storms in the American plains, and there were major issues with an inability to farm and raise crops and feed people. And the Dust Bowl was caused by over-tilling and over-agriculture. So also anything where we have a major loss of vegetation. So again, frequently related to agriculture or sometimes to tree harvesting. So when we cut down all of the vegetation or remove all of the vegetation, the topsoil is less protected and it's more easily eroded by wind and rain. So that's one factor that can degrade soil. Another factor is compaction. So when we drive tractors, bulldozers, large logging machines over soil, that can compress the soil, press it down. If we graze livestock in the same area repeatedly, that can also lead to compaction. And so that reduces the ability of the soil to hold moisture. And that dry soil erodes more easily, supports less plant growth, is more difficult for roots to penetrate. And so the plants that do grow have less developed root structures. And then that leads to more erosion. So this becomes a positive feedback loop of the compaction prevents plant growth, which leads to more compaction, which leads to more dryness, which leads to more erosion, and it makes it even harder for plants to grow there. And then the third thing that can degrade soil is nutrient depletion. This is most often caused by monocropping and lack of rotation. So when we repeatedly grow the same crops on the same soil, it removes key nutrients. Different crops use different nutrients, and some crops actually put some of those nutrients, specifically nitrogen, back into the soil. And so when we grow the same crops over and over again, the same nutrients are depleted. And over time, that soil becomes less fertile and it becomes more difficult to grow crops in that area. Rotation can help to improve this. So this is why we'll talk about leaving fields fallow, allowing them to sort of rest in between. Also to rotation, so growing corn one season, followed by beans, which are a nitrifying organism, which helps to replenish the soil in another season so that we don't have that significant nutrient depletion. Okay, so your first practice FRQ for this is to design an investigation to measure the effect that climate has on soil formation. And as part of your investigation, I want you to identify the independent variable and the dependent variable in your experiment. So we've talked about what soil is and some of the impacts that it has, as well as some of the things that can make it less valuable. Let's talk about what it's made of. So we're going to talk about, as part of this, how much water soil can hold, porosity, permeability, some of the tests that we can do on soil, as well as something called a soil texture triangle that will help us to determine what the components of our soil are. So one of the key characteristics of soil is the particle size, which leads to texture as well as porosity. So the abiotic portion of our soil, or our geologic portion of our soil, is made up of 3 types of particles. And those are sand, silt, and clay. Sand is the largest particle, silt is a smaller particle, and clay is tiny, tiny, tiny particles. So when we talk about soil texture, we're not really talking about how it feels, although how it feels can give us the answer to this. Soil texture is the percentage of sand, silt, and clay in a soil. And so soil texture will always add up to 100% of sand, silt, and clay. So because sand is bigger, we can see that it has bigger pores. There are more empty spaces between the particles. And this allows air and water to enter sandy soil easily. Clay, on the other hand, has the smallest pores, so it's harder for air and water to enter clay-heavy soils. And some of you might have experienced this in your yards or in places that you visit here. We have a lot of heavy clay soils in this area. And so a lot of the time after a heavy rain, we'll see standing water because clay soil does not allow water to penetrate easily. So when we talk about porosity, we are talking about the amount of pore space a soil has. If there's more sand in a soil, it's going to have a higher porosity, which means it's going to be easier for water to get in. If we have more clay in a soil, it's going to have a lower porosity, which means it's going to be much more difficult for water to penetrate. So this is our soil triangle. As I said, our soil texture is determined by the percentages of clay, sand, and silt. So if we look at loam here, we can see that it is 40% sand, 40% silt, and we're going to go straight over here and find that it is 20% clay. And we can check because that should always add up to 100%. So we're always going to start on the bottom with our sand percentage, which conveniently in our testing, sand is always going to settle to the bottom, followed by our silt. And so that would be the next place that we're going to go is out to the side to find the silt number. And then we'll go straight over to the left to find our clay percent. And we want to make sure that adds up to 100%. So we have a little practice activity here. Well, before we do that one, this is our mason jar soil test. You guys are actually going to do this not in a mason jar, but in a graduated cylinder. But we can see that in our mason jar, we have 45% sand. So we're going to go to 45 and we'll come up here. There's 45% sand, 35% silt. So 35, and that puts our line right here, and 20% clay. And so we would identify this soil also as a loam. It's getting more towards a sandy loam because it's not in the center of the loam, but it is still considered a loam. All right, so here's our blue circle, and we're going to practice finding percent sand, silt, and clay. So I want you to pause and try and determine what you think the percentages would be, and then unpause and come back. So we have 30% sand, we have 20% silt, and we have 50% clay. And so overall, we would say that this is a clay soil. 30% sand, 20% silt, 50% clay. It would be very difficult to grow something in this soil because it would be very difficult to get water to our plants. And then when we did get water to those plant roots, it would probably stay there and not penetrate through the soil very well, which tends to lead to waterlogging of the roots, which suffocates them. Okay, so on that, let's talk about porosity, permeability, and water holding capacity. So porosity is the pore space within a soil. If we have more sand in our soil, it's going to be more porous. Permeability is closely related to porosity, but they are not exactly the same thing. So permeability is how easily water drains through a soil. So permeability requires not only lots of pores, but a connectedness of those pores so that the water can move from one pore to the next. But generally speaking, if we have more porous soil, then we're going to have more permeable soil as well. There is a positive relationship between porosity and permeability. Now, water holding capacity is how well water is retained or held by a soil. Water that is more permeable doesn't hold water well. Sorry, soil that is more permeable does not hold water well. So there's an inverse relationship between permeability and water holding capacity. So when it comes to fertility, we want a perfect balance because soil that is too permeable is going to drain water too quickly. It's not going to allow time for those plants to pull water out of the soil, and so it's going to dry out. If we have a soil that is too impermeable, water can't get to the roots, or if it does get to the roots, it sits there, it penetrates, it waterlogs those roots, can actually cause the roots to rot, and it can suffocate the roots because the air also needs to be able to get to roots in order for plants to grow. So our ideal soil for most plant growth is a loam, which balances porosity and water holding capacity. One last important characteristic of soil is its fertility, which refers to its ability to support plant growth. And so that really refers to both nutrients and water. So we've talked about water and ideal soils. It needs to hold water, but not too much water. So we want to have well aerated soil. That usually comes from lots of biological activity. It also is increased with lots of compost or humus or organic matter, because as it decomposes and breaks down, it leaves those little spaces for water to penetrate. We need to have some clay content because that's going to help it to hold on to water, but not too much because that would prevent water from penetrating in the first place. And root structures actually help to increase water holding capacity as well, because roots have little cilia on them that help to make spaces for water to be in the soil. We can decrease water holding capacity by compacting soil, as we talked about, by driving on or having heavy machinery on our soil, or repeatedly grazing livestock in the same location, or erosion of our topsoil, too much sand in our soil, or losing roots. All of those things are going to decrease our water holding capacity. Now, when it comes to nutrients, things like nitrogen, whether that's in the form of nitrates or ammonia, phosphates, potassium, magnesium, calcium, even sodium, all of those nutrients are necessary for plant growth. And so the things that are going to increase our soil nutrient levels are lots of organic matter, because that's going to decompose and release the nutrients into the soil. Humus, which is that decomposed organic material. Decomposer activity, so lots of worms, pill bugs, all those little decomposers whose job it is to recycle those nutrients. But another thing that's important to recognize that increases soil nutrient is clay. And clay generally has sort of negatively charged particles within it. And those nutrients generally have a positive charge. And so the clay actually has, we call it a cation exchange capacity. So it has a higher ability to hold on to the nutrients and then release them to the plants, rather than allowing the nutrients to just dissolve with the water and run away through that alluviation zone. Also having bases in your soil. So a basic parent material like a calcium carbonate or a limestone is going to help a soil hold on to nutrients. Factors that are going to decrease soil nutrient would be acidic soil or lots of acid rain, because those acids are going to leach those positively charged nutrients. We're going to get a high alluviation horizon, and those nutrients are going to be leached out of the soil. If we have too much rain or excessive irrigation, again, anytime we have water, nutrients tend to be water soluble, and so they can leach out of the soil with the rain. We've already talked about excessive farming, particularly without rotation. That tends to deplete the nutrients, and then anything that contributes to topsoil erosion is also going to deplete nutrients in the soil. So some of the tests for soil quality, we are going to test for texture. That's going to tell us the percentage of sand, silt, and clay, which will tell us something about how porous or permeable our soil is. It will also tell us about that cation exchange capacity, so the ability to hold on to nutrients by the amount of clay. We can also test permeability. That's how long it takes for water to drain through a column of soil. High Excessively high permeability and excessively low permeability are both bad for plants. If it's too high, it's going to allow soil to dry out quickly after a rain. If it's too low, our roots are not going to be able to get water, or they're going to be waterlogged. So the optimum is to be somewhere in the middle. pH is another characteristic of soil that we can test. Usually use something super simple like a pH strip. There are also pH testing kits, and this tells us how acidic or alkaline our soil is. More acidic soils have lower nutrient availability. We can also just look at color and compare that. Darker soils have more humus, which means they have more nutrients and more moisture. And then nutrient levels, we can measure ammonium, nitrate, and phosphate levels. And more nutrient levels are going to lead to more plant growth. A low level can indicate that we have either a depleted soil or an acidic soil. And our practice FRQ for this is to identify and describe one test that can be conducted on a soil sample and explain how the results of that test would allow you to give advice to a farmer trying to grow crops in that soil. So that's it for our conversation about soil. As always, I look forward to hearing your questions and talk to you in class.